Hello guys, how are you doing again? Today we're gonna be talking about more moments, but this time it's gonna be moment of a force, vector formulation, moment with respect to an axis, and moment from couples. That's what we're gonna be talking today. And last lecture, just to remember what we were discussing a moment with respect to a point also in 2D, but we were using the scalar formulation. And then remember I said I'm gonna do it in three different ways: the long way, the really long way, the street smart shortest way, but also the way that I want you to do it and work it out. And that was the first one that we work, and basically we apply that moment is equal to force times distance. And the only problem is that on the only thing that we have to take care here is that the line of action of the force, the distance, has to be perpendicular from the point that I want to calculate the moment, perpendicular to the line of action of the force. That's basically what we said before. And you can go back to the previous lecture and read it, but there is a bunch of things involved into calculating this distance L1 and L2. And once you have that, you add them up, multiply that by the force, and that was the value, and then you study the direction, clockwise and counterclockwise. The second method was, okay, instead of me finding the perpendicular distance from the point to the force, I'm gonna keep the force as is, and I'm gonna find the perpendicular component of the force to any known distance through a point that passes through the line of action. For example, the tip here. So this distance, it was easier to calculate, just square root of these two square. And this was the component, the vertical component, or the perpendicular component to the direction, to the distance of that force. But in that case, I needed to find this angle here. And this angle, it was easy to find because this was 20, it was a given, and this alpha here could be calculated based on the geometry. As you can see, the amount of work involved in the calculation was much more smaller than the other one. And the third method, it was applying the superposition principle and the transmissibility, but basically superposition principle. And the important thing about the superposition principle, it was just getting any force, decomposing it in XY components, and then if the force was vertical, multiply that force vertical by the horizontal distance, and if the force was horizontal, multiply that horizontal force times the vertical distance, and then study the movement. And study the movement of the rotation. Remember I told you it's like putting your finger in that point and applying the force independently. Once you do that, that thing was going to rotate in one direction or the other direction at the effect, and that will be the result. So today we're going to start working with moment of a force, but in vector formulation. What happened with vector formulation? Well, if we go to this case, for example, and we have this force and we have a point O, and we have a distance r between the point O and the line of action of the force. Remember we said that moment has to be equal to F times D, but always this F and D should be perpendicular, which is not this case. However, if I make that distance D perpendicular here now, I could say that force times D will be the moment of the force with respect to the point O. Now expressing that D in terms of this R, if I know this angle here, then I can say what? I can say that D is equal to R sine of this angle, and if I get this and I plug it into there, I get that. And if you look this equation closely, you can realize that that equation is the equation for dot product, cross product R cross F. And that's basically what you're gonna do, R cross F. And you study this when you study torque before, in previous classes, and in calc also you study this part, so you shouldn't have any problem doing cross product. Remember, the resultant of a cross product is going to be always a vector, and the resultant of the dot product, like we did before, or we did before when we study projections, it was a number, a scalar. In this case, it's a vector. And the right hand rule is used, remember that, the right hand rule, and I cross j is k and I cross I is 0 because of that equation. Remember, if the angle, if we're using the same angle I and I, the sine of zeta, which is the angle between the two vectors I and I, the angle, that angle is going to be 0. Sine of 0 is 0, so when you multiply two parallel vectors, then the cross product is going to be 0. And if you realize That cross product is taking care of the perpendicularity issue that we had before. So basically any part of the component here is going to be eliminated when we do cross product, which is very good for that. And the right hand rule, remember, apply. I know you know the right hand rule, but I want you also to learn a small circle that I'm going to show you later on how to work it out for doing this multiplication, which is in my opinion easier. Remember here that A cross B is not the same thing as B cross A, and you have to be really careful with this because this is the #1 error when students do these type of problems. So one more time, if you want to calculate the cross product, there are several ways of doing it, but you pivot, you select the pivot point here, and then you say, okay, I eliminate, if this is my pivot element, I eliminate this column and this row, and I say I, that multiplies this times this minus this times this, and then I say minus j that multiplies this times this minus this times that, plus k, eliminate this, and that multiplies this times this minus that times that. That plus or minus, you don't care about that, learn it like that, but that has to do with something which is the co-matrices, co-determinants from this matrix, and basically it's -1 elevated to the n, and n is the addition of rows and columns of the pivot element. But forget about that. You are not going to do anything for now bigger than 3 by 3. So I that multiplies this times this minus that times that, minus j that multiplies this times this minus that times that, plus k that multiplies this times this minus that times that. And that's exactly what you have here. Or this, which is the same thing. Let's do an example to see how you apply this. And the example is says, the man pulls on the rope with a force F of 20 Newton, determine, which by the way, 20 Newton, I don't know, that guy apparently was anemic, because 20 Newton would be like what, 4 kilograms, 10 pounds of force. I don't know, nothing. 4 pounds, it's like 4 pounds of force. So determine the moment that this force exerts about the base at the point O. Solve the problem in two ways, by using the position vector OA and OB. Okay, here I have a discussion moment, and I say, okay, which one is going to be bigger, OA or OB? Well, obviously the distance OA is bigger than the distance OB. Let's see what happens. I don't know what is going to happen. So what are we given here? We're given the force F, and we have the coordinates, meaning I can express that force here, force F, in a Cartesian vector. How do I do that? Well, because you have the position vector that you can create, divide the position vector by the magnitude of the position vector, that's a unit vector, multiply that unit vector by the magnitude of the force, and that's going to be the force in Cartesian component. Now we need R, so we have to find two R's. One, ROA from here to here. Remember last time I told you, whenever you are gonna be working in 3D and we're gonna use in vector formulation, the definition for R is really important. And I say from the point where you want to calculate the moment to the line of action, or to any point in the line of action of the force, from the point to the line of action of the force. So we're gonna do it twice. One R from here to here, and one R from here to here, and compare the results to see which one is bigger. That's basically what we're gonna do. Express the force and the R in Cartesian notation, do the cross product. That's basically what we're going to be doing here. In order to do that, we need the coordinates of this point, the coordinates of that point, and the coordinates of this point. Coordinates of this point, 0, 0, 0. Coordinates of this point, 0 in x, 0 in y, 10.5 in k. Coordinates of this point, 4 in x, 3 in y, 1.5 in k. And this one, 0, 0, 0. How do you find the force F? Find the position vector of the force, BA. How do I find that unit vector? By subtracting 4 here minus 0, -3 minus 0, 1.5 minus 10.5. That gives me the position vector. and divide the position vector by the magnitude of the position vector, which is the square root of the summation of the squares. Once you have the position vector, multiply that, the unit vector, multiply that unit vector by the magnitude of F, which in this case is 20, and you have your force in Cartesian notation. Perfect. You have done this tons of times, so you shouldn't have any excuse for not doing it correctly, at least not any valid excuse. Now, let's do this problem in two ways. So we're going to use the position vector OA, and later we're going to calculate also the position vector OB, because we're going to do it at once. How do you calculate the position vector OA? Subtract the coordinates tip minus tail. 0 minus 0, 0 minus 0, 10.5 minus 0. That's it. Or you can run the vector also. Remember I told you about running the vector before? You start from here and you run the vector from the end, from the beginning to the end. So if I have to go from here to here, I don't move in X or Y, and I just go up 10.5. There you go. If I want to calculate OB, of course it's going to be this minus that one here. Or I can run the vector from here to there. If I do that, I'm going to do this. I'm going to go to the left in X. That means -3. And then I'm going to come to the front. I'm going to come to the front in X. And that happens to you also. I didn't do that on purpose, but that happens to you all the time. So I'm going to come to the front, positive 4x. I'm going to go to the left, -3j. And then I'm going to go up 1.5 in k. This is the value for ROV. And the problem tells us just calculate it in two different ways. So we're going to do that basically. We're going to say R cross F and R cross F. So what do I have here? Remember, cross product, pivot element, I that multiplies this minus this, j, negative j that multiplies this minus that, and positive k that multiplies this times this minus that times that. So for the first case, using the first R, moment is R cross F. This is my force. I calculated that force before. And this is my R. We calculated that R before. We put everything in the determinant, ijk, this and that, and I solve my moment. I that multiplies this times this minus that times that, so it's 0, so only this times this, minus j that multiplies 777 times 10.5 minus 0, plus k that multiplies 0 minus 0. So the answer should be this one here. Usually at this moment I let people copy and I say, do you understand? Yes. Well, apparently not. That is wrong. And I just explained you that several times and repeated it several times before doing the problem. R cross F is supposed to be R cross F. And what we did here was F and then R. So remember what we did and remember what is wrong. This is the most common error when the students solve these type of problems. I did F cross R. What happens if you are solving this in one exam and you got that result over there? Well, you can write and say, listen, I know I messed up with the direction here, but I know also that A cross B is negative B cross A, so the only thing that I have to do is change the direction or the signs of these two coordinates or these two values here, these two components, and that would be my correct result. Or I can do it again, but now I put correctly R and then F and then calculate my moment. If somebody asks you at this point, what is the direction of that moment? How do you express that? Come on, say it. Alpha, beta, and gamma, or the unit vector. You can calculate the unit vector. How do you calculate the unit vector? Calculate the magnitude of the moment and divide each one of the components by the magnitude. That's the cosine of the angles. Cosine alpha, cosine beta, cosine gamma. You should know that. Okay? Now, second part, it says do it with respect to the other R, OB. This R, OB, now we know it. We have the value of F, we have the value for R. And I'm not trying to get you again with the same thing, because I put first R and then F And when I do the multiplication, which is way longer, you see, I get exactly the same result. Now, why the problem is asking you this? For you to realize that it's exactly the same thing no matter what I did. The moment is the tendency to rotate due to the application of a force with respect to a point. The point hasn't changed, it's the same point. The force hasn't changed, it's the same force. So then why the effect should change just because I'm using a different approach? It shouldn't. That's what the problem is trying to teach you. And on top of that, I think personally that you should take another learning from here. Look at, if I use this R, look at all the things involved. If I use the other R, look at the equation directly. So most of it gets eliminated because of these zeros here. In other words, try to get the easiest R that you can use. It's not that it's going to change the result, but it might change the result because probably you're going to mess up with all those multiplications that you have to do there. Once again, look at that thing, 3D, similar to what it was solved before. More cables, the launch pad here, the cables, similar. Cable stay bridges, similar pictures of similar things. Okay, the next topic for today's lecture is going to be moment with respect to an axis, an application. And with the force F, a person is creating a moment MA. What portion of MA is used to turning the socket? Yeah, of course, if I apply this here and I generate the moment here, the moment that is making this turn is actually that component here, and that component follows that axis. What portion of that moment acts on that direction? How much of that moment is used for unscrewing that part? That's several ways of saying the same thing. And I told you last time, every time that a question is asked like that, that implies that you are going to be working with projections, dot product. So the moment with respect to an axis is calculated in the same way that you calculate the projection of a vector with respect to an axis. Once you know the moment, you just dot multiply by the unit vector of that axis. For example, if we had the same problem that we did before, but now the problem has another part, and the other part say, oh, by the way, on top of calculating the moment with respect to the point O, I want you to also calculate the moment of that force, but not with respect to the point O, but with respect to this axis, A prime. And about that axis, the only thing that I know is that axis passes to the point O and passes also to the point 340 here. How do I do that? Easy peasy lemon squeezy. What I told you before. You just get the moment with respect to any point in the axis, which we already have, and you do a dot multiplication with that moment and the unit vector of that axis. Meaning, and remember, this result is going to be a number, because it's basically doing the projection of that moment, but now with respect to this axis. I don't know if you realize that I'm talking about moments and I'm putting a double tip arrow here. Yeah, that's commonly used to separate the moment with vector moment from any force vector, for example. And force vector you use one tip, and moment you use two tip, but it's basically the same thing. So what are we doing here then? Finding the unit vector A prime. How do you find the unit vector A prime? Well, I have the point 0, 0, 0, and I have the point 340, so I can find the position vector, which is 3.0 divided by the square root of 3 squared plus 4 squared. This is the unit vector. And the only thing that I do now is I dot multiply this and that. You can do it like that, so I times I plus j times j, and then you get your A prime. Easy, once again. Easy, easy. This is, I will advise you to do it in this way if the problem is in like two parts. First, find the moment with respect to a point, and then finding the projection of that moment with respect to an axis that also passes through the point. Then you can do it by parts. However, you could do this problem using also something that is called triple scalar product. And the triple scalar product is basically when you want to find only the component of the moment with respect to the axis at the end, and you don't need to find any moment with respect to any point. So basically what you do is this. You put first, instead, remember ijk, r, and force. Now you put the unit vector of the axis, the arm, and the force. In this case, of course, you need the unit vector. Remember this point here, it was 340, and we calculated here, look, the unit vector before. So that's my unit vector, 0.6, 0.80. So I'm gonna use that, 0.6, 0.80. And then I have 0, 0, 10.5, that's my R from here to there, and that's my force. Why is this? Because I need, first, the unit vector of the axis. Second, the arm from any point belonging to that axis, and any point in the line of action of the force. So the point O, for example, yeah, it's part of the axis. And the point A belongs to the line of action of the force. So basically, I can do that. Or, what if I decided to go from the unit vector, again, the same unit vector, but now instead of going from here to here, OA, I go from here to here. Well, that point also passes through the line of action, meaning I can do that like that. Then I have unit vector, R, and force, and the result should be the same. Now, at the same time, what if I want to, instead of doing this like that, what if I want to say, okay, I know this point here is 3.340. What if I decided to go, and that point belongs to the axis, and the only thing that I'm looking, I'm not interested in the point O at all. The only thing that I'm looking is, what is the component of that force, with the moment of that force with respect to this axis? Well, if I know that point, I can say it also, you know something, I'm going to consider this my R, and I'm going to do it like that, and I know this is my R, right, because from here to here, that will be my R, 3 minus 0, 4 minus 0, 0 minus 10.5, that will be my R, I'm sorry, this one, 0 minus 3, 0 minus 4, and 10.5 minus 0, that will be my R, and this is F. Or what if I say, no, I want to do it from this point to this point, which is also one point in the axis and one point in the line of action of the force. I can do that also and calculate this R and apply the same unit vector of the axis AA prime. This is the R from here to here, and this is the force, and I will get exactly the same result. Important thing, you can do it in two parts or one part. If you're doing by parts, first you have to calculate the moment of the force with respect to any point that passes through the axis that you are interested in, and second, dot multiply the unit vector of the axis with that moment that you calculated. That's the two-stage calculation. One stage calculation. Find the unit vector of the axis. Unit vector of the axis. Find the distance from any point, and remember this, any point along the axis to the line of action of the force, which is this, or the other two that we did before, and the force in Cartesian formulation, and do the triple scalar product. And the triple scalar product is this that multiplies this times this minus this times this, minus this that multiplies this times that minus this times that, plus this that multiplies this times that minus this times that. And that's the way you do it. The last topic for today is going to be a moment of a couple. And a couple is defined as, in this case, a couple means two of the same, or similar at least, two of the same. In this case, a couple of forces is defined as two forces, two parallel forces. Of course, parallel forces meaning not acting in the same line, not collinear. Parallel forces, not slanted forces, parallel forces, and opposite to each other, same magnitude and opposite to each other, exactly what you have there. Why is that? Because if we do that, the result of those two forces multiplied by that distance is gonna be F times D. That's gonna be F times D. Let me ask you something here. I'm gonna switch to the top camera. Look, let's prove that. This is really easy to prove. So let's say that I have this force F, and I have this force F here, and the distance here is D. But the problem, or what the statement is saying, is that the moment is equal to F times D. Is that correct? Well, let's see. Let's say that I am standing here. Let's say this is the point A, this is the point B. Let's say that I'm standing at the point A. So if I'm standing at point A and I say moment with respect to the point A, what is the moment with respect to the point A? This force is not producing moment because passes through the point. The only force producing moment is this one. So it's going to be F times the perpendicular distance, which is from here to here, which is D. And the direction of rotation, if I apply this force, the direction of rotation is that. Meaning the direction of rotation is this, meaning that is clockwise. Let me see clockwise here. Clockwise, I'm going to say positive. Just for the sake of saying positive. Usually people say negative, but I don't care. Positive. Or clockwise. Okay? Positive. Because then I'm gonna use it later. Let's say that I do the moment, if I do summation of forces in X direction, then I have positive F minus F equals 0. The only result is F times D. It's a moment, pure moment. Now, what if I say summation of moments at B here, or I calculate moment at B? Force, this force doesn't produce any moment because it passes through the point F. What about the distance? The distance is D. What about the direction? If I do this, it's gonna come in this way, meaning this way, and that way is counterclockwise or is positive in my case. Now, no, wait, but this is too weird. I'm gonna select the middle of that point. The middle of that point, and I'm saying the middle for saying the middle. I could say the third, the half, what the fourth. This distance is the half, and this distance is the half, and I'm gonna call that this point C here, C. What if I do now summation of moments at C? Moment at C. Well, first, remember superposition. Let's divide and conquer. Let's apply first this one. F is the force, and the distance from here to here is D half. And the direction is this, and that is positive. Positive. Now let's study the other one. This force here is going to be also F multiplied by the distance, and the distance is D half, and the direction is this, and this direction is like that, and that is also positive. F D half equals F times D. So still is F times D. Oh, no, wait, you are cheating here. Okay, instead of doing that now, what if I calculate it here, and I say, oh, this distance now is D, and I'm gonna calculate this with respect to the point E, for example, here, at this point, and I'm gonna say the moment at D produced by that couple. What is the moment at D produced by that couple? Okay, let's start with this force first. Force multiplied by, what is the distance from here to here? It's gonna be a small d plus big D. And the direction is this, and that is clockwise, and I say clockwise is positive. Okay? Now let's study the other force independently. Force is F, and the distance is big D. and if I push this, it's gonna go in this direction. That direction is counterclockwise. Counterclockwise, according to whatever convention I just wrote here, is negative. If I solve for this is gonna be fd plus fd minus fd, cancel, cancel. Moment with respect to, this is not d, this is e, equals fd, which is the same here, 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 everywhere. In other words, whenever you have a couple, the result of a couple is just a pure moment, nothing more. Summation of forces is zero always, they cancel out, and the only resultant from a couple is a pure moment. Keep that in mind, and let's do this example. It says two couples act on the beam. One couple is formed by the forces A and D, A and B, these two forces, and the other one is forces C and D, okay, here. If the resultant couple is to be zero, determine the magnitude of PF and the distance D between A and B. Okay. Resultant couple. Resultant couple. Another word for couple, and I want you to translate it like that, basically, is eliminate couple and change that word for moment. So if it's like that, then you're going to say two moments act on the beam. One moment is formed by the forces A and B, and the other moment is produced by the forces D and C. If the resultant moment is zero, determine the magnitude of PF and the distance D between A and B. Period. It's easier to read. Okay, let's see what happens here. This force P, what is a couple? Couple of two forces equal. The problem is telling you this is a couple. So if this is a couple, these two forces are parallel. Yes, they are parallel, and they have the same value. So the value for the P is 500, and the value for F is 300, because those are two couples. This is a couple, and this is a couple. Now, what other thing says? Summation of moments equals zero. So here we have two ways of doing it. This is the first part of the problem. Now, what is the summation of moments has to be zero? Well, remember, a couple is F times D. Okay, F times D meaning the moment, I can select a direction. In this case, I'm selecting counterclockwise as positive. So the moment generated by this couple is 500 times 2, and it's gonna rotate clockwise, as you can see there. So basically, this one here, I'm gonna do this in the camera document. Let me copy this really quick here, because I think it's easier for you to follow it in that way. So if I have this problem, which is the problem that I'm trying to solve here, and I have this here like that, and I know this is 500 and this is 500 here. This distance is given as 2 meters, and this is Newton. And then on top of that, I have this one here, and I have this one here, and this is 300, and this is 300, and this angle is 60, which is given. And of course, if this is 60, this is 60, because, and this is 30, because these two have to be parallel. So if I know the resultant moment has to be zero, because that's one of the things that the problem is saying, and I know the moment generated by these two, I'm gonna say once again, to follow the same material that I posted over there, that this is positive. So if this is positive, this easier to do it when you have a couple. Just put your finger at the center and apply both forces at the same time. You see, both forces at the same time, and you see the rotation in that way. So this is rotating in this way, opposite to this one, meaning this is gonna be negative. Force 500 times distance 2 meters, distance between the two forces. Done. Now plus this other one. Remember, when we have force times distance, force and distance, let me put it here because you can see me, or you can see it because of me. Force times distance, force and distance has to be perpendicular. Okay, so then I have to convert this into this force and this component here. And I have another component for this force, one going in this direction and one going in that direction. This angle here is 30, and this value here is going to be 300 cosine 30 degrees, which is the same value here also, 300 cosine 30 degrees. And the distance from here to here is provided as d. So to this part, these two forces produce a couple, which is going to be the force 300 times cosine 30 degrees multiplied by the distance, which is d. And how much is this? Well, the direction first is in this way, and that way is this way, and this way, according to my convention, is positive. And the problem states that the summation of forces has to be 0, meaning that from here I can solve for d and say is 500 times 2 divided by 300 cosine 30 degrees, and that would be, how much is that? 3.85. I could have solved this problem differently, and instead of what happened with these two? Well, this is gonna be f sine 30, and this is gonna be f sine 30. But these two components are collinear, so I have negative f sine 30, positive f sine 30 in the same line. It's like having two effects here, one pulling in this direction, one pulling in this direction. Both of them cancel in that line, so it doesn't produce any moment effect. And if you do summation of forces, this plus this plus this plus this is 0 also. 0. There's no force, pure couples, moment. Now this problem I could have solved it differently also, because I could have gotten this problem here and say, oh, remember the one we did before that I say instead of finding the distance perpendicular to the force, I can have the force perpendicular to the distance? Well, I can do something like that. In this case, I have something like this, and this is d, and I know this distance here is 60, and I know this is 300, and this is 300. Well, what if I decided to come here and find this perpendicular distance here? I know this value. How much is this value? This value is this value, and this is the same 60 degrees. And I know that this is 60, this is 90, this is 30 degrees here. And if this is 30 degrees and this is d, this value here is d cosine 30 degrees. So what is this couple here? This couple here is going to be 300 times d cosine 30 degrees, this one. And it's going to be rotating in this way, and that way is negative. And if I add, that way is positive, I'm sorry. And if I add this one, the one that I had before, which is a negative 500 times 2, and I solve for d, it's going to be the same thing, 500 times 2 divided by 300 cosine 30, which is the same thing that we got here. So you can go and check this on your own, but please redo it because it's important for you to go and check it again. Now, last problem for today is the same thing but now in 3D. It says express the moment of the couple acting on the pipe in Cartesian vector form, and what is the magnitude of the couple moment? Well, these two are a couple. Those two are perpendicular. One is positive k, one is negative k, and I have all the distances. So basically the only thing that I have to do is find this distance from here to there. But because this is in vector, let's treat it as Cartesian. This is 3D, let's treat it as Cartesian. And I'm gonna do moment either with respect to this point or with respect to this point. Let's say that I'm standing at B. If I want to do moment, it's gonna be r cross f. R cross f. So this distance here is 1I. This distance here is 1.5 j. This distance here is 2I, and this distance here is 1j. Put it together, that's the r that I have. Cross multiply by this one. Remember why I'm saying that, because I'm saying moment at B. This doesn't produce any moment with respect to B, and this is my R, and this is my force, which is negative because it's pointing down K. Once I solve for that, you can use this circle. This circle is really good for that, and I still use it when I'm doing, instead of using the determinant, I'm using this circle, and I say, I just mark I, J, K, and I say everything that goes in this direction is positive, everything that goes in the opposite direction is negative. So if I say I cross J, it's gonna be K, but if I say I cross K, I go against the flow, you see. I cross K is gonna be negative J. This is a way of doing this without the determinant. The determinant is going to give it to you directly, but this you can do it like applying the distributive property if you want to. So if I'm going to apply the distributive property, I say I cross K should be negative J, but I have this negative here, so it's going to be positive J. 3 times 20 is going to be 60, positive J. And now you have J cross K. J cross K should be positive I, but I have a negative sign here, so it's going to be negative 2.5 times 20, 50I. There you go. And that would be the moment in that case. What if I decided to step here and say, okay, I'm going to do, instead of moment at B, moment at C. If these are a couple, it shouldn't affect at all. And you know what is going to happen? This force won't produce, and then my R is going to be all switch. So this is going to be negative, 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 but my force is going to be positive K. So basically I'm switching these signs here, and the result should be the same result. What if I want to know what is the direction of this? Alpha, beta, and gamma, or unit vector. That's the way I know the direction of this. Okay, that's sufficient for today, and it was another video that I thought it was going to be shorter, but lectures take time. It's not all about solving problems, it's about understanding the concepts. So next class, well, if you want the magnitude, you take the square root of both of them. So next lecture, we're gonna start working with equivalent systems, resultant of force, and coupled system, but this is not for today. This is for next time. So wake up, guys. See you next lecture. Have a good day. Where are you?